All right, class, welcome to section 2.7. That's a mistake right there. Absolute value functions. All right. So last section in this chapter, we are going to simply go over the absolute value functions again. We have discussed them in chapter 1 extensively. We have transformed them. We've done a lot of problems on that. We want to get a little bit more practice and this time concentrate on absolute value functions only. So in the last section, we discussed how to solve absolute value equations and inequalities. And maybe we can even use that knowledge now to graph absolute value function. So here it is one more time, just like we discussed in the last section. The absolute value of a function is the same, the absolute value of a number is the same as the number if you plug in a positive value. So we discussed the fact that on the positive side of the x-axis, the graph of the absolute value function looks just like x. So it's a piecewise defined function. So again, the absolute value of a positive number is itself. However, the absolute value of a negative number, so if x is a negative number you plug in, you must take its opposite. So on the negative side of the x-axis, we draw the function negative x. So it's a downward looking line. Yes, the slope is a negative one, so it's going down. So if you remember again from our library of functions in 1.3, this famous V-shaped is what the absolute value function looks like. So if you also think about transformations of our regular original functions, we call these toolkit functions or parent functions or simply basic functions, then any other absolute value function will have the same V-shaped. It though might be narrower, it might be shifted up, left, right, and so on and so on. So let's see one more time. However, yes, the most significant feature, yes, of the absolute value graph is this corner point of the V, right? So if we could tell where the corner point is and how narrow, right, or where this graph is going, we pretty much have the graph. So let's just go through a whole bunch of problems and see how we can, one more time, graph an absolute value functions. We're going to use two methods. Either by using transformations, which is what we have practiced in chapter 1. So here it is. We are starting again with, we are starting with the absolute value function. Yes, this is an absolute value function. So we must transform the graph of the absolute value function. So I'm going to draw my basic absolute value function. Then what sort of transformations are there performed? So remember, I always like to start with the x transformation. So the absolute value of x minus 1 means just move the graph 1 unit to the right, so the opposite way of what it says to x. So we simply shifted this graph 1 unit to the right. The next step would be to multiply this by 2. So again, it's going to go in the order of operations. So multiplying by 2 simply means multiply all the y coordinates by 2. So this corner point again has a y of 0, so it stays. This y coordinate is a 1, and now it moves to a 2. So what that does is really changing the slope of both these arms of the V to a 2 rather to a 1. So it's a vertical stretch by a factor of 2. So it gets twice as wide. or as narrow actually, right? It's twice as long vertically. And finally, the last transformation would be to add the 3. And adding the 3 takes this last graph we had and moves it 3 units up just as it is. So it's still just as narrow vertically as the blue graph. It is just a copy of it shifted 4 units up. So we have the 3 transformations. Again, x minus 1 in the absolute values made the graph shift 1 unit to the right. Then multiplying that graph by 2 simply made the y values multiply by 2. So that caused the graph to vertically stretch by a factor of 2. And finally, the plus 3 makes the graph shift up 3 units. So this is the final graph we have. Now, how else could we have graphed this function without performing all these transformations? Well, maybe we can find the corner point, and then intercept. So same as we drew the lines, we actually drew lines 2 different ways. If you remember when we first started talking about them in 2.2, all we did is just try to find the intercepts. In other words, substitute a 0 for x, find the y, substitute a 0 for y, find the x, right? Okay, so let's see if we can do the same things here. Now, if I plug in a 0 for x, I'm going to get 2 times the absolute value of -1. The absolute value of -1 is a positive 1. So you see I'm going to get a 5. So in other words, this graph is going to cross through the y-axis at 5. Okay, we have 1 point on the graph. Actually, if you see, that's the point right here. Now, to make y equal to 0, that means I need to solve this equation. So solving this absolute value equation, as we learned last time, we would minus the 3 from both sides, divide by 2, and so if you remember what we learned last time is that once we isolate the absolute value, which is the first thing you have to do when solving an absolute value equation, we look across the equal, and if we do have a negative number, that is a warning sign right there, because an absolute value can never equal to a negative, yes? So in other words, the y's can never equal to 0. That's never going to happen. And as you see, this graph we have never has a y equal to 0. This graph starts up here on, it goes only as low as 3, so it will never equal to 0, right? So we already know our graph is not going to cross through the x-axis because y can never equal to 0. So that didn't help at all. Now the problem is, if this is my only method and I already don't know what the graph looks like, I'm kind of stumped, because with 1 point only, I absolutely cannot draw this V-shaped, right? Where will it go? Great, it goes through this 1 point, but how narrow? Where? Upside down? What do I do? So at this point, we already know at least the graph is never going to cross through the x-axis, but that's pretty much all we have to go by. So we could try and plot in more points and try and start guessing what happens, but that's the best we can do at this point. So I'm going to start plugging in more points and see what happens. So plug in a 1. And I don't really have much room left here, but if I plug in a 1, I'm going to get a 0 inside the absolute values. So 2 times 0, 0 plus 3 is going to equal to a 3. So I know I have the point of coordinates 1, 3. Okay, well, that's better. I can plug in a 2, and same thing. Here, I'm going to delete this here. Plugging in a 2 inside the function, then I'm going to have 2 minus 1 is a 1. Absolute value of 1 is 1, so I'm getting 5 again. That is very helpful, and we were lucky because we came back up to 5. So due to the nature of how the absolute value function has to be symmetrical, right? So these two V bars look exactly the same, left and right of the corner point. So because this point is right in the middle and we ended up getting back up to 5, I know that this is the graph of the function, okay? Because again, it has to look symmetrical. So since we got the bottom piece of the V right here, I know the graph is going to keep on stretching. And we know that because we know the graph, the shape of this absolute value function. So I'm saying that we're lucky because we immediately got to close the V, and then we knew how the graph was going. If the corner point was somewhere down here, it would have taken us a while to get there. So I'm kind of also trying to express to you that using transformations, in fact, is the fastest and best way to graph these kind of functions, because we should, and again, that's if you do know by now how these transformations work, right? We practice quite a bit on that. So let's try this again. So let's graph it again, this next function, using transformations. All right. So using transformations one more time, I am going to start with our basic function, that is the absolute value graph. And it's cornered at 0. It has a slope of 1, which is why I'm going nicely halfway through this first quadrant, halfway through the second quadrant. That's what the absolute value looks like. Okay. Now the first transformation here, again, I always like to start with the transformations on the x. And because it says 2 times x, I'm going to do exactly the opposite. So I'm going to divide all the x coordinates by 2. This x coordinate is a 2. I cut it in half. And the same thing here. So all these points are really coming in towards the y-axis by a factor of 2. So the graph got compressed horizontally by a factor of 2. That's the transformation. Okay. And there's one more transformation right here that says y is the absolute value of 2x. So the red graph we had before, right? It's just the graph from before, but then minus 3. So minus 3 means take that graph as it was and move it down 3 units. So it's going to be just as narrow as up above, just shifted down 3 units. All right. So let's see if we can guess or we can graph this function one more time. This time finding intercepts and the corner. So here is my function. I'm going to write it in front of our noses. And we want to graph this function by finding intercepts. Okay, so I'm going to get started right here. Substitute 0 for x, find the y, then substitute 0 for y and find the x. See how we're doing. So if I plug in a 0 for x, I'm going to get 2 times 0, 0, absolute value of 0 minus 3 is a negative 3. If I plug in a 0 for y, that simply means f of x equals to 0, right? So, or y equals to 0. Solving this equation, as we learned to do in the last chapter, or section I should say. First things first, you need to add 3 to both sides, right? Then explain what this absolute value means. We have two choices, either 2x equals to 3 or 2x equals to negative 3. Each of these would get me one answer. So setting y equal to 0, so setting this function equal to 0, gave us two answers, 1.5 and negative 1.5. So we have 2 points. I don't want to graph on the same coordinate system. I'd like to start over again with these points. So one of them is 0, negative 3. The other two are 1.5 and 0 and negative 1.5 and 0. So does that look exactly nicely symmetrical? Yes, it does. Okay. So halfway between negative 1.5 and positive 1.5 is where you're going to find your corner, and then halfway between negative 1.5 and positive 1.5 is 0. We do have the point when x is 0. So in other words, that is our corner right there. And so yes, with these 3 points and what we've learned last time about, again, solving absolute value equations, we can indeed graph graph this absolute value function just by finding these few points. But still my favorite is the transformations, if you ask me. So let's try this one more time. I've given you here 2 transformations. See if you can remember how they work, and if you can do this by yourself, but here it is. We're going to start one more time with the absolute value function, which I'm trying very nicely to go exactly through halfway, the quadrants. So in other words, I'm going on a slope of 1 over 1, okay? I'm going to always go to the transformations inside. So the absolute value of x plus 3 makes the graph go in the opposite direction of the plus. So in other words, we're going to go left 3 units. And here it is. And finally, the negative 1/2 multiplied to the function makes all the y values multiply by a negative 1/2. So take all the y's you've had before and multiply them by a negative 1/2. Well, this y is a 0, so times negative 1/2 stays at 0. This y is a 1. When I multiply it to negative 1/2, it flips over. It flips over the y-axis. So again, the fact that we're multiplying by over the x-axis, so the fact that we multiply by a negative makes all the positives y's from before negative y. So this graph flips over the x-axis, yes. And it becomes multiply by a half. That simply means a vertical compression by a factor of 1/2. So the graph gets squished in vertically. Okay, and here is our final answer. All right. Now one more time, let's see if we could have graphed this function otherwise, just by finding the appropriate points. Okay. So not too much that we could do. Again, it's a pretty funny equation that we'll end up solving. So first things first, easy. Always you can plug in 0. You will always get an answer. So when I plug in a 0 for x, 0 plus 3 is 3. Absolute value of 3 is 3. So we're going to get negative 3/2 or negative 1.5. So this is the y-axis intercept. X is 0, y is negative 1.5. Okay. All right. Now if we set the equation equal to 0, because now we want y to equal to 0. So we said that instead of the function f of x, we put a 0 in its place. Now let's see what's going to happen. Okay, again, divide both sides by negative 1/2. That's still a 0 because 0 divided by any non-zero number gives you 0. And so in this case, we actually do not have two choices because there is no plus 0 and minus 0. There's no such thing as a negative 0. So our only option in this case is if this absolute value equals to 0. So in other words, there's only one choice, and that would be negative 3. Okay, so we have only one solution. So let's see if we can get a graph or if we can get an idea of how many more points we need. Okay, so I have the point of coordinate 0, negative 1.5. And I have the point of coordinates negative 3 and 0. So with these 2 points, we're not quite sure which one's the corner, right? How is this graph going to go, right? How is this V going to look like through these 2 points? Of course, in our transformations, if we look to the left, we know very well what is happening here. So what I'm saying is that you will need to plug in a little bit more value. So we know what happens at negative 3. Maybe go a little bit more and plug in more points. So I'm going to see what happens at negative 6. Really, the best way to do is set the function equal to negative 1.5 and see if you can find the other x value, but it's always easier to pick x's and just plug them in. So what happens if I plug in a negative 6 for x? Well, I'm going to get a negative 3, and absolute value of negative 3 is a positive 3. So there's your negative 1.5, which I knew I was going to get. And so because of that, we do know that this 0 is our corner point. The other reason how I knew that 0 is the corner point is because I'm not crossing it 2 times. See how I knew there is no other crossing point through the x-axis? That means this must be my corner point, okay? Because if we had the corner point somewhere else, anywhere, the graph would have crossed 2 times. Okay, so I hope that makes sense. And again, one more time, what did we do here? We chose another value, and we got the same y coordinate. Okay. So therefore, we knew the corner point must be halfway through 0 and negative 6, and that makes it the negative 3 is our corner point. And again, a lot better because you keep the shape, you keep the corner, and you see where it's moving. A lot faster would actually be to know the transformations and use them for this specific function. There you go. All right, so let's see if we can go backwards. It always helps to go back and forth and see if we can find an equation for the function graph. And we've also played with these back in chapter 1 when we talked about our transformations and we tried to say, hey, here is what happened to the absolute value function. Can you write an equation for it? So looking at this graph, I immediately can tell that it's an absolute value function. Yes. All right. What else can I tell? I can tell that my corner, which is normally at 0, 0, this is my basic function, has shifted where? Has shifted to the right 3 units. So therefore, I have to have an x minus 3 as a transformation to x. So again, this story could have come to you in chapter 1 as we take the absolute value, shift it to the right 3 units. You see it on the graph here, yes. It doesn't have to be spelled out to you because you see it, right? And then the graph is also moved down 2 units, so therefore we minused 2 from the function. But not only that, you see that this graph is not going 1 up, 1 to the right, 1 up, 1 to the right. It goes 2 up, 1 to the right. So therefore, this graph has also been stretched vertically by a factor of 2. So these are your 3 transformations, kind of like what happened in the first graph. Yes, it got stretched vertically by a factor of 2. So see how the slope is now a 2 over 1. So we go up to 1 to the right. And then it shifted 1 unit to the right and 3 units up. So let me draw another. It's hard to make these stay in place. So here, let's see if you can determine what the equation for this function is. And again, as always, I'm suggesting you should be pausing these videos, try and graph the functions yourselves, and then come back and see if you've gotten the right answer. So I'm going to move on, and right away, here it is. It's an absolute value function. What happened to it again, it got shifted 3 units from the 0, 0 normally is 3 units to the right, this time 2 units up. But then also what happened to this graph, and it got flipped about the x-axis. The slope is the same, it's the 1 over 1. So it did not get narrower or wider, but it got flipped, which is why all the y values got multiplied by a -1. And here it is. The end of chapter 2.